Hello, everyone. A very warm good evening to all of you, and welcome to Unacademy. Welcome to the final session of the Fundamentals of Physical Geography, where today we are going to talk about the details of oceanography in terms of the oceanic waves which are generated, the tidal movements in the oceans, and also the case of your ocean currents. So, that is our overall discussion for today. We are going to take a detailed look into each of these aspects, individual oceans, trying to understand what is a Gulf Stream, how does that get generated, and more such aspects associated with the ocean currents, which is the most important portion. From here, questions are asked in the prelims, the type of currents, cold currents or warm currents. Questions are also repeated in the mains examination. For example, what are the forces which end up generating the ocean currents, both in the optional as well as in the GS. Now, this session basically culminates our overall discussion for the NCERT. All of you who have basically attended these sessions, who have gained something out of that, now, or even if you think that you have read the NCERTs, you don't need to attend the session. For all of you, we have a test. Okay. So, complete NCERT test for geography. Now, here you will get the prelims focused questions, right? It will be a kind of a revision test which will be held on 9th of August at 7 p.m. That is the same time. You can scan the code and you can enroll for the test. And if you end up scoring well, if you end up being in the top 5%, now, thereby, there are rewards associated, and you get additional 20% discount on the upcoming platinum batch of geography. From next week, we are going to start the detailed discussion of geography, building up of the concepts of these NCRT series and going into the further requirements of the examination wherever possible as well. So, for that, do avail the discount. In the platinum session, you also can avail one to one mentorship with the educators themselves. You have the super mentors, the people who have actually cleared the examination. They shall also be guiding you about how to frame your schedule, how to prioritize the study of the subject. So that is where platinum will always be beneficial for you. And performance of this NCRT will help you avail that course at a very cheap price, get the guidance by the educators also. So, having said that, we move on to the PYQ. Now, the PYQ, which was asked in 2021, take a look at that. Consider the following statements. In the tropical zone, the western sections of the oceans are warmer than the eastern sections owing to the influence of the trade winds. In the temperate zone, westerlies make the eastern sections of the oceans warmer than the western sections. Which of the statements given above is or are correct? No, platinum is a different batch, Mayur. Platinum is where you have the camera on from the side of the students also, and you have the educator as your mentor, who will be meeting once or twice a month, and you will have a super mentorship as well with the people who have cleared the exam. Okay. Now, what is the answer for this? In this, the first statement is in the tropical zone, western sections of the oceans are warmer than the eastern sections owing to the influence of the trade winds. Is this statement correct? The answer is yes. This particular statement is correct. Why? Why in the tropical zone, western sections of oceans will be warmer as compared to the eastern sections? Owing to what we discussed yesterday, that if you have these trade winds, on the eastern part of the continents, they will end up causing upwelling, meaning a lower sea surface temperature. Whereas on the western side of the continents, they will end up causing downwelling, which increases the sea surface temperature. So, this is basically owing to the upwelling and the downwelling. So, this is correct. The second statement, in the temperate zone, westerlies make the eastern sections of the oceans warmer than the western sections. In the temperate zone, you will find that the westerlies they will make the eastern sections of the oceans. Here you will have downwelling. So this will end up being warmer, right? So this statement is also correct. So the correct answer is going to be C. That is both 1 and 2. Okay. It is a simple concept that we discussed yesterday associated with the concept of onshore and offshore winds. Onshore winds end up creating downwelling, which increases the sea surface temperature, and the offshore winds create upwelling, which reduces the sea surface temperature. Okay. In subtropics, the salinity decreases with depth, and that would mean that density also decreases with depth. No, not always so, right? So, Divesh, basically, please understand when you talk about the density of oceanic water, density of oceanic water is determined both by temperature as well as salinity. One of them is not the only factor. And always understand whenever you have both the competing aspects of salinity as well as temperature involved, in that particular case temperature gains precedence in determining the density of oceanic water. For example, if we talk about the case of the tropics, now tropics, the salinity should be very high, right? Salinity should be very high means density should be high, because salinity directly determines the density. But in the tropics, the temperature is also very high. Temperature is very high means the density should be less. So if you consider the temperature factor, density should be less. If you consider the salinity factor, density should be high. So what is the actual density of oceanic water in that region? So that is why always remember this. Whenever you have both the factors competing with each other in terms of determining the density, always you will have the temperature factor which takes precedence, because higher temperature means even the salt particles which are there, they will also get energized, they will also move away from each other, so there will be a larger space available between the particles, which means a kind of a lower density. Okay, I hope that is clear. Now, so basically today we are going to talk about the case of the movement of oceanic water. Now, when we talk about the case of oceanic water, it has got various different movements, temporary as well as permanent. When we say temporary, for example, when you see the case of the waves, now these waves are generated on a daily basis, on a minute by minute basis, on an hourly basis. You see the generation of these waves in the larger oceans, larger seas, etc. Now, this does not carry water sufficiently from one end of the spectrum to the other. That is why these are temporary movements. Because if you observe this animation very carefully, what do you observe? Observe any section of water here. Let's say you fix your eye on this section of water. Observe the movement which is associated. It comes back to its original position. So, this is a kind of a temporary movement. Right. Now, why is this kind of a motion created? This kind of a motion will always be created due to the impact of the surface winds. You have winds which move in the atmosphere, right? Now, these winds, imagine this as the sea surface. On top of it, if the winds are moving, the winds will have a frictional drag. With that frictional drag, they will try to pull up some water along with that. But obviously, the winds are not so powerful enough. This water will be dropped. In the meanwhile, the wind energy will pick up water from somewhere else, and that will be pulled. Right? So, this water which has come down will try to come to its original position. So, that is where you have the case of a continued wave motion. Now, think about it. Why do we say that it is repetitive? Waves, we always say, is a repetitive motion. So if you observe this image, you will basically observe the motion, right, Observe the motion that the particles they go through. The motion is oscillatory, repetitive, oscillatory, all impacted by the wind. The region where, let's suppose, you have had a kind of a wave here, this uprised portion is what is known as the crest of the wave. And this downward motion is what is known as the trough of a wave. So every wave will have a crest and a trough. But this portion which has risen up will also tend to fall down. This portion which has fallen down will tend to rise up. So eventually, what do you come across is after some time, the wave motion will be like this. So the crest will be replaced by a trough and a trough to be replaced by a crest. So this is the repetitive motion associated with that of a wave. Okay. Now, when we talk about these waves, right, it is the wind energy which carries them through. But there are certain terminologies that you should be aware about. Crest and trough, we have already talked about. Wherever you have the rising phenomena, that is a crest. Wherever you have the sunken phenomena, that is known as the case of a trough. Now, if this was the normal height of the sea, let's suppose the wave has generated a crest and a trough. This difference in height, what is the maximum height that the crest can take? That is what is referred to as the wave height. Okay, that is associated with a wave height. Then, overall, the difference is also what is referred to as the amplitude of the wave. This is your wave amplitude, the half of the overall height. That is the case of the wave amplitude. So, wave height from the lowest portion to the highest portion. This is your wave height. Wave height. Okay. This portion is your amplitude. Okay. Now, the time period between two of the crests, right? For example, the wave is like this. So, how much time this crest takes to get transferred here by the wind? That time period elapsed between the two crests or the two trough of a wave, that is what is known as the period, the wave period associated, and that is also your wavelength of the wave. Okay, the speed at which some of the water can move is also what is referred to as the wave speed. Now, when you stand at the coastal area, you basically do observe that the sea waves they come in and then they go back. Most of you would have observed this. So this is also a phenomena associated with the wave, right? In the coastal area, the wave comes in and then it goes back. So this forward motion of a wave is what is associated as swash. Okay. When the wave moves forward, that is what is known as a swash. And when the wave moves backwards, that is a backwash. Oftentimes, if you stand in the coastal area, if let's suppose you have kept some of your goods, your goggles, shades, or some of the water bottles, etc., if the backwash is very strong, it carries it along with it into the sea, right? So, backwash oftentimes is driven by the gradient of the land, that how the slope of the coastal area is. Depending upon that, the backwash can be very strong or can be very, very weak. In most of the areas, you will observe that a swash is followed by a backwash. Every time, for example, even if this starts going back, you will observe that after some time, again a swash comes, right? That is what you observe. However, across the coastline, there are certain areas where there is no swash, only backwash. Why and what is that? So these are the phenomena which are known as your rip currents. Okay. So what is the rip current? So in certain areas, you will observe that the backwash is so streamlined and with such a significant flow that it is continuous. These are the most dangerous areas in the coastline. You come across the news story that few tourists who were there at the beach, they somehow got drowned, even though they knew swimming, but they basically were not able to survive because they were dragged to the middle of the sea. This is a rip current. It occurs in certain areas across the western coast of India. That becomes very common. So, why is this phenomena generated? And what is this phenomena? So, this phenomena is always generated owing to the topographical variation in the sea floor. Okay. For example, let's suppose you consider the sea floor like this. Let's suppose you consider the sea floor like this. Now, in this area, let's suppose you have some of the sand deposits here. Okay. You have sand deposits. And here also you have sand deposits. But in between them, you have a gap. Okay. So the ocean water comes here, creates a swash. But for the ocean water, it is always easy to return from this particular gap. So, regardless of the fact that swash is created anywhere, this region will consistently have a backwash that generates a continuous backward flow or a rip current. So, observe this. This is the real life image in certain areas. You will always find that swash is happening from here or here or here or here. All of them generate a backwash only from one place. That is why, if let's suppose you get trapped in this, getting saved from this rip current is absolutely almost impossible. The best of the swimmers out there, they lose their lives into this, right? Because it tests your stamina. The sea is continuous, the wave is continuously dragging you into the center of the sea. And as a panic reaction, what does a human do? As a panic reaction, you will try to swim to the coastal area, right? And you will put in more and more amount of effort and more energy, but the wave continues to drag you backwards. Eventually, you will lose your energy, and that is when you will begin to drown. That is why always advisable in the case of a backwash that you basically try to swim sideways, so that if let's suppose you move to the sideways, you are saved from this backward current. So this is associated. Why? It is associated because the topography of the continental shelf in this region, right? Topography of the continental shelf in this region would have had such kind of a variation. Okay. So if this is the coastline, this is the beach, this is the level till which you have the sea water. So under the sea water, this is the kind of a topography. I hope this image creates a better view. Here you observe that under the water, you have this gap which creates a consistent backwash. So that is basically your rip currents. Okay. So that is the factor associated with the waves. Now, what are tides? Oftentimes, you will find the general population, they will mistake or they will confuse waves with tides. Why western coast? Because western coast is a submergent coast, and that is where you have multiple such tectonic faults, divides, etc., which create certain channels. For example, if ever you move from the region around, let's suppose, to the north of Karnataka coastline, right? And you move from Mangalore, Udupi northwards, you will find these areas associated to the south of Goa coastline. You will find such areas. One particular notorious region is the Turtle Bay, beautiful scenic location, but then very dangerous in terms of water. It can end up creating much greater depressions over a long period of time, Manisha. Correct. Okay. Now, most of the population you will observe, they will refer to waves and tides as the same thing. But tides are very different as compared to waves. Waves are what? In the case of the wave, this was the seawater. This seawater was disturbed into a crest and a trough by the winds. But in the case of the tides, if you observe this, sea level rises up and sea level basically falls down. So it is a kind of a periodic rise and fall of the sea level. Sea level increases. In many areas, it comes inwards into the coastline. In certain cases, it goes absolutely backwards. For example, when you consider the Odisha coastline, in the coastline of Odisha, you have a region named Chandipur, very famous because near Chandipur you have the missile testing site of India as well. Now, Chandipur is also famous. Why? Because there you will observe that if this is the sea level, let's suppose, normal sea level, during high tide, the water comes like this, and the shape of the coastline is such during low tide, the water comes here. So the difference, this is what is your the condition of a high tide, high level of water, and this is your low tide, right? So this is known as the high tide line, and this is known as your low tide line. So the difference between the high tide line and the low tide line in Chandipur is many kilometers. So that is where you will observe that the water flows back quite substantially. It is dependent upon the shape of the coastline as well. So you observe that the sea level rises. Sea level rises to a point that is your high tide. Okay, that is your high tide line. Then the sea level also falls during the low tide. That is your low tide line. Okay, so this will be your low tide line. This will be the high tide line. Okay, so that is the difference, right? UPSC had asked this question about Chandipur in the prelims of 2017 as well. That in which part of India do you experience that during the low tide, the sea retreats for many kilometers? Okay, so that was the case of Chandipur. Okay, now the difference between the difference between the high tide line to the low tide line, that is known as the tidal range. So it is basically a difference between high tide line and low tide line. Okay, now why do we have these tides, and where do we have these tides? Everywhere it is not the same, it varies. For example, Gulf of Mexico experiences high tide and low tide only once a day. Bay of Bengal experiences high tide and low tide twice a day, right? Arabian Sea experiences high tide and low tide twice a day. So that is the case of your variation in the tides. How do we get these tides? So when we consider the factors influencing tides, you have two major factors. One is the case of the gravitational pull of both sun and the moon. Another is the case of the centrifugal force. What is centrifugal force? We will discuss it in greater detail, but any object moving in rotational motion experiences a force acting in the outward direction. That is your centrifugal force. Okay. So, centrifugal force is also responsible for generation of tide. How? We will take a look into it. Gravitational force is also important. Gravitational force is basically acted upon by both sun and the moon. But out of both of them, the gravitational pull exerted by the moon is much more powerful. Why? Because moon is much more closer to the earth as compared to the case of the sun. So that is why moon's gravitational force will have a greater impact. It will have a greater impact. Okay. Now, because of the proximity to planet Earth. Now, when we talk about these tides, you see, basically the side which is facing the moon or the sun, there the gravitational force will be much higher. Let's name these sides differently. Let's name these sides as 1, 2, 3, and 4. Now, can I say that the gravitational force will be maximum at 1? Can I say so? Gravitational force will be minimal at 3? Can I say so? So, gravitational is maximum at 1 means it will try to pull it. But then the continents won't be pulled. The continents are very solid, very massive, very bulky. The continents can't be pulled. But the water, which is interconnected across the planet, that water will be attracted by the moon. So that creates a kind of a bulge. That means the level of water in this entire region goes high. This is what is also referred to as a tidal bulge. This is what is referred to as a tidal bulge. Yes, Deepika, correct. Now, where does this excess water come from? Is it the case that suddenly the oceans have got more water to generate? Is it the case that suddenly more water is poured into the oceans from the rivers? No. This tidal bulge will be supported by water coming from 2 and 4. They will be able to support this tidal bulge. So that is where this area will experience a high tide, one will experience a high tide, but 2 and 4, the water level goes down. That is the region which will experience a kind of a low tide. Okay, that is the region which will experience a kind of a low tide. So that is the reason for the generation of a tidal bulge. On the opposite side, however, can you imagine planet Earth being stable in this particular shape? Can this shape be stable for planet Earth, a planet which is rotating? It will always try to gain a spherical or a symmetrical shape. In order to gain that symmetry, many of the times, planet Earth develops a kind of an opposite bulge of slightly less volume, but nonetheless a kind of an opposite bulge. This is what is also referred to as a counter bulge. Counter bulge. So, like that, you have two areas experiencing high tide and two areas experiencing low tide. For example, in this case, follow this marker. Okay. Follow this marker 1. Okay. Observe that as it is facing the moon, it will experience a high tide. As it is basically moving in the direction of the perpendicular to moon, it will experience a low tide. Observe and correlate it with the water level. When it is facing the moon, high tide. Gravitational force is very high. When it is facing this region, a low tide, right? Because that water will be used to support that high tide. When it is absolutely opposite, there again, some amount of high tide. Why high tide on the opposite end? Why this counter bulge? This counter bulge has been generated primarily in order to gain a stability, a similarity in rotation, but also the other reason is the reason of centrifugal force. So let us summarize this. Tidal bulge is generated due to the gravitational pull, isn't it? Gravitational pull. Now, the counter bulge basically is generated why? For two reasons. One is the case of symmetry, right? I am simplifying it as symmetry. Actually, the reality is for conservation of angular momentum in order to have that stability and stable mass. Conservation of angular momentum. Momentum. And then the second reason is you basically will have the role of centrifugal force. How? Let's take a look into this. How the role of centrifugal force comes into play. Okay, let us analyze that. Now, what is a centrifugal force? Any object rotating in circular motion will always experience an outward acting force. Okay, now let's suppose you have a bucket of water which is spinning. Okay, a bucket of water which is actually spinning. Now, when it spins, the centrifugal force will act in the opposite directions, away from the center, isn't it? Always. The same site will not get high or low tide, always it will rotate. As in, okay, please understand one thing. Let me elaborate it in a more simpler manner, if possible. Let's suppose this is your planet Earth. Okay, let's suppose this is the case of your planet Earth. Here you have the moon. Okay, let's name this place 1, 2, 3, 4. As of now, which areas will experience a high tide? For high tide, you will have 1 and 3. Low tide, 2 and 4. I hope this is clear. High tide will be 1 and 3, and 2 and 4 will be experiencing the low tide. Yes. For one complete rotation, planet Earth takes how much time? 24 hours for one complete rotation, almost 24 hours, isn't it? So, in 6 hours duration, I will have a situation where 1 has reached here, 2 has reached here, 3 is here, 4 is here, moon is here. Moon is also moving ever so slightly, but let's not include that variable. Now, which will have a high tide? High tide will be 4 and 2. Low tide will be 1 and 3. In how much duration? 6 hours. Why only 6 hours? Because one complete rotation will take 24 hours. This is quarter of a rotation that I am considering. That is one fourth of the complete rotation that I am considering. Are we able to understand that? Now, again, after 6 hours, what is the position of the planet Earth that I will have? One will come here, two will come here, three will be here, four will be here. This is the position of the moon. Which are the areas which will experience high tide now? High tide will be experienced by 1 and 3. Low tide will be experienced by 2 and 4. What is the duration? Again, 6 hours. So, 1 and 3, they are experiencing high tide and low tide after a duration of how much time? 12 hours. 6 plus 6, isn't it? Again, in 6 hours, basically, I will have 1, 2, 3, 4. This is my moon. So, which will experience high tide? 2 and 4. Low tide? 1 and 3. Again, a duration of 6 hours. So, are you observing this? That planet is also rotating, right? Planet is rotating. So, 1 and 3 will experience high tide and low tide after every 12 hours. 2 and 4 will also experience high tide and low tide after every 12 hours. I hope we are able to get this. Yes or no? Yes. Is that clear now? That how they will have the condition of a high tide and the case of the low tide? Yes, Sudhanshu, correct. So that is basically explained by this animation. Look at the hours here now. Now you take a look at the hours. So start with the first position here. After, at 6 hours, you observe the low tide. At 12 hours, again a high tide. 18 hours, again a low tide. 24 hours, again a kind of a high tide. You observe this? So that is basically because the side facing the moon will always face the kind of a high tide. The side exactly opposite to the moon will also experience a kind of a high tide. Is that making sense? Anyone having any kind of doubt? Do let me know. No doubt? All water bodies on planet Earth? No. No, Revati. Majority of the water bodies. There are certain other variations associated with the shape of the coastline, position of the sun, etc. But basically, for a generic aspect, you can always consider that yes, water bodies, seas, and oceans, they will experience high tide and low tide twice a day, right? That is why, in general, closer to the equator, you will observe that uh, at around 12 in the noon and 12 at night, you have the condition of high tide. 6 a.m. in the morning, 6 p.m. in the evening, you have the condition of a low tide. Okay. This is always the case in most of the situations. Then there is some latitudinal variation, some shape of the coastline, but that is the technicality of the tides I don't want you to get into. I just want you to understand the basic concept of the tides. How do the tides get generated? There are multiple theories in geography also associated with the tidal formation, right? Just like in the case of continent, we had seen you had the continental drift theory, convection current theory, seafloor spreading theory. Then came the plate tectonic theory. Similarly, in the case of tidal formation, also, you have the coastline theory, you have the wave transition theory, you have the solar propagation theory, you have multiple theories associated with the tidal force generation as well. Okay, I hope this is clear, right? How the tides get generated. It is the gravitational pull. When you are facing the moon, there is a tidal bulge. That tidal bulge is supported from two of the sides. So those two areas will experience a kind of a low tide, right? Those two areas will experience a kind of a low tide. So this tidal bulge is a bit higher. Observe this image carefully. You will observe that this tidal bulge is a bit higher because it is facing the moon. Okay. In order to gain symmetry, there is an opposite tidal bulge of a slightly less magnitude, but that is just to gain symmetry. Now, where is this water being provided for 1 and 3? From the regions of 2 and 4. That is why 2 and 4 will have the case of low tides. If this is clear, let me know the case where if tidal height is higher at 1, low tide will be lower or higher. What will be the impact of on the low tide? If let's suppose the high tide is higher, what will be the impact on the low tide? What do you think? Low tide will be much more lower. Okay, low tide will be much more lower. Why? Because more water is going to support this condition of a high tide. Okay, so higher the height of the high tide, lower is the height of the low tide. Now we come to the second case, that is the case of the centrifugal force. What is the centrifugal force? Any rotating object experiences a force acting away from the center, and that is known as the centrifugal force, right? Now, when you consider the case of the planet Earth is consistently rotating on its axis. So, there will be a centrifugal force acting in all directions, away from the center. Now, while this will not influence the position of the continents, it will definitely influence the water bodies, right? The simple analogy is that of a bucket. If you hold the bucket with a rope, fill it with water, and let's suppose you rotate the bucket, water will swirl outside due to the centrifugal force. So, similarly, when you have the planet which is rotating, centrifugal force will be acting in all different directions. A combination of gravitational force and centrifugal force, the addition or subtraction, any of them, a combination of both of them is going to lead to what is known as tidal generating force. Meaning what? Let us understand this. So, consider the case of the Earth, right? Now, this is your moon, this is your planet Earth, right? Now, this is basically reverted. So, let's consider here this is your the region of the moon. Okay, ignore this. This is your moon. Now, moon will have a near side and a far side. If I name this as 1 and if I name this as 2, gravitational force at 1 will be greater as compared to gravitational force being experienced at 2. Yes or no? Because 1 is facing the moon, is facing the moon. Yes. 2 is away from the moon. Right. So here, in the region of 1, gravitational force of moon is going to be greater than the centrifugal force. At the region of 2, centrifugal force is greater than the gravitational force of moon. Why? Because 2 is far away, exactly to the opposite of the moon. So gravitational force extended at 2 will be very, very less. Yes or no? Simple concept. Simple concept, what we had discussed earlier as well. If this is the planet Earth, this is the moon, moon will extend its gravitational force, right? Gravitational force will be high at 1 and will be minimum at 2, isn't it? Centrifugal force will be equal everywhere. So that is where you will find that at the region of 1, both gravitational force and centrifugal force add on to each other, whereas at 2, the addition is less. That is why counter bulge is slightly of lower height as compared to 1. Okay. Then you have the classification of tides, right? The classification of tides on certain criteria. How do you categorize or classify the tides? So tides are classified in on basis of two categories or two bases. So when we talk about tides, classification is on the basis of position of sun and moon, because sun will also have its own solar bulge it will create. And second is the case of frequency, how frequently the tides occur. Okay, correct, Sudhanshu. At 1, gravitational force prevails over the centrifugal force. At 2, centrifugal force prevails. That is why the height is comparatively less, but it's a high tide nonetheless. Okay, so when we say on the basis of position, this has got two types: spring tide and neap tide. On the basis of frequency, it is diurnal and semi-diurnal. Let us understand what is spring tide, what is neap tide. So, understand and look at this very carefully. Take a look at the first position. In the first position, sun, earth, and the moon, they appear to lie on the same plane, almost on the same axis also. Right? Now, here you will observe that the sun will create its own small bulge, the inner bulge that you see, that is the solar tide. The moon will also create its own bulge. Now, in this case, what will be the impact on the high tide? High tide will be higher than normal, or will it be lower than normal? What do you think? What will be the impact in terms of the case of the high tide? Yeah, just a moment. Yeah. In this case, because both of them will be added on to each other. So that is where you will have high tide is higher than normal. Higher than normal. Right? When high tide is higher than normal, because both the forces are combined, what will be the phenomena of the low tide? We have discussed just now. So low tide will be what? Normal, higher than normal, or lower than normal? It will be lower than normal. Perfect. This condition is observed under two circumstances. When you have both the sun and the moon on the same side of planet Earth, or Earth in between and moon on the other side. This is known as the condition of a spring tide. Spring tide. Okay. That is a condition known as the case of a spring tide. Okay. By the way, this position whereby the earth, the sun, and the moon, this position, when all of them are in a straight line, this position is also what is referred to as syzygy. When all of them are in the straight line, that is what is also referred to as a syzygy. Now, when the moon is opposite to the earth, this is the opposition position of syzygy. This is known as opposition. And this position is known as conjunction. So syzygy has got two positions, conjunction and opposition. In both the cases, spring tide will generate a high tide higher than normal, low tide which is lower than normal. By the way, what will be the time period between conjunction and opposition? Or what is the time period in which you experience these spring tides? What is the time period? How frequently will you experience this? So it is based upon the rotation of moon. How much time does the moon take to have a complete movement across the earth? It takes almost how much? 12 hours. Very good. So in 12 hours, if you have a high tide which is higher than normal and low tide which is lower than normal, so then that means a place will always experience spring tide only. Is it the case? No. This is basically the moon's position when the moon will move. Okay. Moon takes how much time for a complete movement across the entirety of Earth? It happens every 28 days. So that means every 14 days, the moon will be either here or here. So the gap between spring tide is every 14 days. Okay. I hope you understand that. Please do not get confused between the rotation of Earth and the movement of the moon. Okay. What all of you guys who have told that it will be 12 hours, you have considered the rotation of Earth. That Earth will rotate, right? And thereby you have immediately said 12 hours. But what you have not understood in this case is in case, in case there is a condition where you have to rectify this, do let me know. IQ2316J3J, does spring tide occur twice a month? How many days are there in a month, my dear? How many days are there in a month? 30 days or 31 days? Spring tides gets repeated after how many days? 14 days. So can I say it can occur twice a month? Yes or no? Or whether do we have a confusion between what is greater, 14 days or 31 days? I hope you have the answer. Those of you who immediately said 12 hours, what you are getting confused in is that if this is the position of the moon, or this is, let's suppose, the position of the moon, right? Earth is rotating. So 1, 2, 3, 4, you basically said that one will experience high tide and two will experience low tide. This is the condition every day, right? This is the condition which is experienced every day. But once a while, it will happen that high tide will be higher than normal and low tide will be lower than normal. When will that happen? That will happen when the moon is in the same region as the sun, in the same axis as the sun. Then the lunar and the solar bulge gets added. That is known as the condition of a spring tide. Now, sometimes it will happen that moon is perpendicular to the position of the sun. This is a position which is known as a quadrature. In the condition of a quadrature, observe the case of the solar tide. This is your solar tide. Observe the case of the lunar tide. This is your lunar tide. Yes or no? So, if you observe, as per the solar tide, this region should get a low tide as per the solar tide condition. But as per the lunar tide, here you have a bulge, isn't it? So they will cancel out each other. That is when high tides will be lower than normal because they get cancelled out. Okay? Because they will get cancelled out. The impact of the sun and the impact of the moon will cancel out each other. What about the case of the low tide in that case? Will the low tide also be lower than normal? Yes or no? In that case, the low tide generated will be higher than normal because less amount of water is consumed in creating a bulge. Okay. What is the time duration? So, such conditions are known as the conditions of neap tide. What is the time duration between a spring tide and a neap tide? So, overall, the moon will take 28 days for a complete rotation. So, from here to here, it will take 7 days. After 7 days of a spring tide, you will have a neap tide. After 7 days of a neap tide, you will again have a spring tide. After 7 days, again a neap tide. After 7 days, again a spring tide. So, here, basically, you have the conditions of high tide being different from every day, low tide also being different as compared to every day. This is clear, yes or no? Are we able to understand that how it will be different? Yes or no? Clear? But sun has more gravity than moon, then why the tide is lower? Distance plays a major role. Moon is much closer to us. That is why the impact of gravity on the water body is much higher. Revati. Okay? Right. So I hope this is the portion which is absolutely crystal clear. Now observe the case with the help of the animation. The yellow color surrounding the planet Earth is the impact of the solar tide, which is almost consistent. Okay? During neap tide, sun and the moon and the earth, they are at right angles to each other. So observe, whenever the sun, the moon, and the earth, they are at the same axis, they are at the same line. Both the high tide, solar high, the solar tide and the lunar tide, both the high tides combine. So that is the condition of the spring tide, right? After 7 days, you will observe there is a condition where the position of the moon is perpendicular. The condition which is known as quadrature. And in the condition of quadrature, what do you observe? They will cancel out each other. So that is a condition of a neap tide, right? In neap tide, height of the high tide is comparatively lower. Is this clear? I hope this is understood. So this is basically the formation of these tides based upon the position of the sun and the moon, which is different from normal conditions. So just to clarify again, let's suppose you consider any particular region. Let's suppose you consider the region like the Bay of Bengal, right? If you observe the coastline of Bay of Bengal, let me remove all of this. Okay. If you, let's suppose, consider the coastline of Bay of Bengal. Now, this is the sea level. Okay. During the condition of high tide on a daily basis, let's suppose the sea level rises to here. During the condition of low tide on a daily basis, let's suppose the water level comes here. However, twice a month it will happen that the high tide level will be here. This is the case of a spring high tide. When will it occur? New moon, right? Whenever you have new moon, in those cases, you have a spring high tide. In those cases, even the low tide will be lower. That will be your spring low tide. Then there will be the condition twice a month when you have a quarter of the moon, which is half of the moon which is visible. That is the first quarter, when the high tide will be comparatively lower than normal. This is your neap high tide. And the low tide will also be slightly higher than normal. That will be your neap low tide. Okay. So under normal circumstances, you will only have the condition of the high tide and the low tide under normal circumstances. But twice a month it will happen that the high tide is higher than normal. In that case, the low tide is also lower than normal. Twice a month it will happen that it will also be the condition of a neap tide. I hope now it is much more clearer. Okay. Then you have the classification of the tides based upon the duration, the frequency. So basically, most areas generally have the condition of two high tides and two low tides experienced each day, with both the high tide and the low tide having the same height, right? That is, the high tide will have the same height and the low tides will have the same height. That is known as the semi-diurnal, that they get repeated half a day in because every day you have two such occurrences, so they get repeated every half a day. That is semi-diurnal. So in Bay of Bengal, for example, you will observe two high tides and two low tides. Then in certain areas, for example, Gulf of Mexico, every day only one high tide and only one low tide. That is known as diurnal, daily. Daily one high tide, daily one low tide. What is it dependent upon, or why is this variation? So this variation is dependent upon certain factors. One is the case of the geography of the coastline, whether the water is being channelized or not, geography of coastline. Okay. Then, other than that, it also has to do with the case of the latitude, solar position. Okay. Then, opening to the sea. So, that is the variation that you will end up observing in these particular areas. Okay. Wherever in general you will observe that the water has to be directed through a narrow channel. In that case, in general, you will have one high tide, one low tide in a day. Wherever it is slightly more open to the connected to the larger ocean, twice a day it will move up and down. For example, Bay of Bengal, almost connected to the southern Indian Ocean, as is the case with the Arabian Sea. So as the Indian Ocean gets moved up and down, Bay of Bengal will also experience that. But observe the geography of the region of Gulf of Mexico. Now, in the region of the Gulf of Mexico, if I remove all of this, observe here. This is your Atlantic, isn't it? Now, through the barrier that is the Antilles and the Caribbean islands, here you have the Yucatan Peninsula, and then you have the opening through the region of Florida. So here the water has to come through. If Atlantic experiences the rise and fall twice a day, that easily doesn't get translated into Gulf of Mexico. Why? Because the water, once it is channelized through here, indicating a rise or a fall, that in itself has got a lag. It is redirected there. There are multiple barriers, correct? So that is why it is the geography of the location which has got, and the coastal shape. For example, even if you observe this one, the case of the Hudson Bay, there also you will not find the exactly semi-diurnal tide like you observe in Bay of Bengal and Arabian Sea. In Bay of Bengal and Arabian Sea, absolute semi-diurnal you will observe, right? Twice a day, because it is open, right? For example, South China Sea, you will observe semi-diurnal, open to the Pacific here. Okay. But those narrow channels, there you will have some of the barrier associated. I hope it is making sense. Then we come to the movement in the ocean. Oceanic water tends to continuously move in a certain direction. You have a kind of a unified flow, continued unified flow, whereby large volumes of oceanic water are continuously transported from one region to another. Those are known as ocean currents. Okay. Factors determining the high and the low tide: gravitational pull by the sun and the moon, and the case of centrifugal force. Okay. So when you basically observe that the oceanic water, there's a kind of a continued movement in the oceanic water in a certain direction. Okay. So that is basically known as ocean current. Ocean currents are classified as or referred to as regularized movement, fixed direction of flow, large volumes move in a defined path. What you observe on your screen is the eastern coast of North America. Okay. And here, this is one of the strongest ocean currents across the planet Earth, that is known as your Gulf Stream. So that is the case of ocean currents. Ocean currents have a larger impact on the climate of a region. They are instrumental in creating deserts in many parts of the world. So ocean currents are also vital for trade and navigation. In earlier times, they would help people in moving from point A to point B easily. Now, when we talk about the types of currents, you have the classification of currents based upon the depth as well as based upon the temperature, depth and temperature. Okay. So, based on the depth, you have the classification as surface current, the Gulf Stream, Norwegian current, etc., that you come across. All these are surface current. And then you have the deep water currents or the deep currents generated due to a phenomena known as thermohaline circulation. Based on temperature, you basically have cold currents. Just like the winds, you have the cold winds and the warm winds. Similarly, you have cold currents and the case of warm currents. Now, surface currents, they are present only up till around top 100 to 400 meters from the surface. The depth of the ocean is how much? Almost 4 to 5 kilometers. These are driven by heating, cooling, winds, etc. The deep currents, they are basically the dominant one, present across the depth for many kilometers, generated because of density differences. Density differences, salinity differences, temperature differences, that is what generates the deep currents. Okay, so as you can see, surface current is restricted only to a portion. Deeper currents are present in much deeper, or the depth currents are present in much deeper regions. Now, based upon temperature, you have the case of cold current. Cold current means what? They are colder. Temperature is colder, right? When you say a cold wind, do you associate a temperature to a cold wind? That it has to be 5 degrees Celsius, 4 degrees Celsius, etc. No. When do you say a wind is cold? If your region has been experiencing 45 degrees Celsius temperature, if the wind is even of 35, you will consider it to be cooler. If your region is experiencing 20 degrees Celsius, a wind which is 10 degrees Celsius will be colder. So it is always comparative. Whatever is the normal condition in your area, if the ocean water is colder than that, it is a cold current. Okay. So generally, cold currents, they bring water, or they basically bring cold water into the warm water regions. So movement is associated from higher latitudes to lower latitudes. Okay. Movement is associated, any ocean current which moves from higher latitude to lower latitude, they will bring colder water in comparison, right? That is a cold current. They are usually found on the west coast of the continents in the low and middle latitude. Why? That is because on the west coast of the continents, across both the in the lower latitudes, you will experience what is known as upwelling, right? In the region, here you have the case of, in these latitudes, you have trade winds. Now, trade winds in the west coast of the continents, they are offshore. And offshore trade winds will generate what? Upwelling means colder water, and that means the current, ocean current, will also be cold current. Okay. The PYQ that we did in the first part of the session itself, it is associated with the same thing. Okay. So observe it in the lower latitude, right? This is the east coast and the west coast. So this is the west coast of the continent. This is the east coast of the continent. This is the west coast of the continent. So here you will have upwelling. Here you will have upwelling. So colder water, right? And here you will have downwelling. Here also you will have downwelling. So you will have warmer water. So warm currents are going to be present across the east coast of the continents. Cold current are going to be present across the west coast of the continents. So what are warm currents? They bring warmer water into cold water areas, or generally, whenever you have ocean current from lower latitude to higher latitude. Okay. Whenever you have the movement of ocean current from the lower to higher latitude, it is generally associated with the case of a warm current. Okay. So it is observed in the east coast of the continents. Why? In the east coast of the continents, the trade winds, they end up becoming onshore, and these onshore trade winds will basically create downwelling. Downwelling will basically mean sea surface temperature increases, and the increase in sea surface temperature will mean that you have warm current. Okay, that is how you have generation of warm current. But how are these ocean currents generated? What are the forces? So broadly it is classified into two parts. You have the case of the major forces or primary forces, and you have secondary forces. So what are the primary forces? Primary force, one of the major primary forces, the case of heating by the sun or solar insolation. Insolation. How? So you see, in the lower latitude, let's suppose you consider the sea level. This is your equator, 0 degree, and this is your 90 degree. Okay. Heating by the sun in the lower latitude is always going to be very high. And that heating means expansion of water is created. Water tends to expand ever so slightly in this region. Colder region are particularly compressed water. So there is a expansion, a height gradient. Oftentimes a height gradient of around 8 centimeter is created, right? 8 centimeter of height gradient is created in the lower latitude. And that generates a natural flow from the lower to the higher latitude. So solar insolation is a prime factor. But how do the winds move? In which direction will the winds move? That is decided by the permanent winds or the prevailing winds. That is the trade winds, the westerlies, the polar easterlies. They are associated with the wind pattern, which will generate the ocean current. Now, secondary factors. Now, if an ocean current is moving, I have shown you the animation of the ocean current. You will observe that they don't always move in a straight line. There is a kind of a circular motion in many of the cases as well, isn't it? So here, basically, you will observe one of the secondary factor, major secondary factor is the influence of the Coriolis force. Coriolis force ensures that any ocean current moving in the northern hemisphere will bend in the rightward direction. Any ocean current moving in the southern hemisphere will bend in the leftward direction. So if you consider the planet, if you consider the equator, if an ocean current is moving like this, it will have a rightward bend. Ocean current moving here will have a leftward bend. Okay, that is the impact of the Coriolis force. Then the other factor is shape of the coastline. Of the coastline. Okay. Then other factor is bottom relief. For example, mid-ocean ridges, sea mounts, etc. They will also create a kind of a bifurcation or the division of the ocean currents. Okay. So these are basically the major and the minor factors. There is the force of gravity as well. But gravity is more involved in the thermohaline circulation or the deep ocean currents. In surface current, the role of gravity is very minimal. Okay. You can consider the role of gravity in the sense that the solar insolation has created the height gradient. So that has allowed from a greater height to a lower height the movement. So that is where you can consider the role of gravity. But otherwise, okay, otherwise, these are your major and the minor factors. Okay. So take a look at it that basically the ocean bottom relief oftentimes can lead to the division of the ocean currents. Shape of the coastline ensures that the ocean currents they get divided in this region. No, Coriolis force and centrifugal force, they are very different. They are very, very different. Centrifugal force is the force acting outwards. Vinita, did we miss out on the portion of Coriolis force where we discussed the planetary winds? I think we have missed out on that. Coriolis force, why is it that the Coriolis force acts in any moving object? Because of the differential speed of rotation. That is why the Coriolis force acts. Okay. So please take a detailed look at the lecture of the planetary winds, the permanent wind systems. We have discussed in great detail about the case of the Coriolis force. What is Coriolis force? Why does it act? Okay. Shape of the coastline, observe. IQ here, observe here that basically, if you look at the ocean currents, because of the shape of the Gulf of Mexico, the ocean currents are coming like this. Because of the here, the Floridan Peninsula, the ocean current comes like this, right? Because of the shape of the coastline here around Bay of Biscay, it will move like this. So, shape of coastline can always influence the direction that the ocean currents will take. Okay, is that clear? Bottom relief factor, mid-oceanic ridges, etc., can also divide the oceanic movements. Wherever, let's suppose you have mid-oceanic ridges, ocean current is coming, it can easily get divided because of the barrier. Does tide have an influence on ocean current? No. Tide is a daily phenomena. Ocean current is a regular phenomena. It continues to happen. Okay. So during that ocean currents, this tidal movement will always get generated. Okay. Now, if you take a look at the ocean currents in the Atlantic Ocean, if you observe here, this is mistaken. This is your equatorial counter current. Okay. So you will observe that the trade winds first, what they do, they will generate a north equatorial current and they will generate a south equatorial current. This will be generated by the trade winds. All the warm water will accumulate here. Some of that warm water will flow back, and that generates an equatorial counter current. Okay. Shape of the coastline will ensure that the ocean currents here they come like this. You have the Antilles Islands. So you have the greater Antilles current and the lesser Antilles current. They move through like this, through the Yucatan Channel, into the Gulf of Mexico. They meet with the Antilles current here. This is known as your Florida current. Florida current. And that is when they generate the strongest ocean current, the warmest ocean current anywhere across the planet. And that is what is referred to as the Gulf Stream. This Gulf Stream, as it moves further northwards, there is a cold ocean current coming from the higher latitude, that is your Labrador current. Here you have the mixing of the cold and the warm ocean current. Wherever you have mixing of the cold and the warm ocean current, cold and warm ocean current, in those areas, you basically will observe ideal fishing grounds to be created. There you will observe the formation and the creation of ideal fishing grounds, very rich in the supply of fish. Then this warm current further moves, and there you have the North Atlantic drift, which keeps the region ice free during most of the year. It is further subdivided into Norwegian current. You have a warm current going here also, in this region also, known as the Irminger current. It has multiple classifications. Coriolis force ensures it will bend to the rightward direction. Now the water is coming from higher latitude to the lower latitude, and that is where you have the Canary current, the cold Canary current, because it is coming from a higher latitude to the lower latitude. Okay. If you observe the southern hemisphere, same thing, just that it bends in the leftward direction. Here you will find the Brazil current. It mixes with the west wind drift, the cold current around Antarctica carried by the westerlies. It will again bend leftwards, creating the cold Beniguela current, because again, moving from higher latitude to the lower latitude. This is how ocean currents are generated. The same principle is followed in the Pacific as well as Atlantic. However, in the Atlantic, there is some slight difference. In the central portion, you have a zone of calm where lot of seaweed grows. And that is the seaweed in Portuguese is known as sargassum. That is where this portion is also associated with lot of seaweeds known as Sargasso Sea, famous as the only sea across the world where no coastal landmass lies. Sargasso Sea is surrounded by ocean currents. Gulf Stream and Labrador current, they mix around the region of Nova Scotia, that is around the region of Newfoundland, that is very good for fishing, yes. Observe the ocean currents in the case of the Pacific. The trade winds, they will basically generate the north equatorial current and the south equatorial current. This north equatorial current will then bend rightwards owing to the Coriolis force. They will generate the warm ocean current, the Kuroshio current, similar to the Gulf Stream, slightly slower in terms of its intensity, but similar. Around the Tsushima island, you have the Tsushima current, which will be generated. From the region of the Bering Sea, a cold ocean current comes. That is the Oyashio current. So here again, you will have the mixing of the cold and the warm ocean current. Ideal fishing ground. Fishing ground. Okay. Then, like there, you had the North Atlantic drift. Here you have the North Pacific current. It moves, it gets divided. This goes to the higher latitude. Any ocean current moving from lower to higher latitude will be a warm current. So, warm Alaska current, but a cold California current. Here also, a counter equatorial current is generated. Okay. Now, Indian Ocean, however, is different. Northern Indian Ocean, not the Southern Indian Ocean. Northern Indian Ocean is different. Why? Because unlike the Atlantic and the Pacific, Northern Indian Ocean is closed. Does cold and warm flow clockwise or and there is no such set pattern for cold and warm. Clockwise or anti-clockwise is determined based upon the hemisphere, right? So there is no such set pattern. That warm current will move in clockwise, cold current will move in anti-clockwise. Okay. So if you observe the case of the southern Indian Ocean, it is quite similar to the southern Pacific and the southern Atlantic. You have the south equatorial current, which gets generated. You have the Mozambique and the Agulhas current, mixes with the west wind drift, the circumpolar Antarctic, bends to the left, bends to the left, and you have the circulation. But in the northern Indian Ocean, it is surrounded by landmass. So here the wind factor becomes very dominant. And the wind basically reverts itself as well, particularly in the month of advancing monsoon, that is May to August. What do you observe? Direction of the winds is towards the Indian coastline, the southwest monsoon season. So observe the ocean currents are clock, clockwise. But then, if you observe during the month of October to December, you have the retreating monsoon and the northeast monsoon. So the ocean currents in the northern hemisphere accordingly change the direction. Primarily because you have the case of the water body closely surrounded by the landmass. Okay? Now, these are the case of the ocean currents. Ocean currents, they have, and this is the detailed map associated with the ocean currents. You can refer to it in the PDF also. Impact of ocean currents. How do they influence? So, first of all, they help in trade and navigation. Trade and navigation, right? They allow for the movement of ships from one region to another. Then they help in temperature, right? They influence the temperature. Cold ocean currents will lower the temperature. Warm ocean currents can increase the temperature. Then fishing conditions, wherever warm and cold ocean currents meet, ideal fishing grounds. Then create deserts. Wherever you have cold ocean currents, in those areas, they create deserts. Always. How? So observe. Here you have the cold Peru current. Here you have the Atacama Desert. You have the cold California current. You have the case of the desert, the Mojave Desert in the region. Cold Canary current, Sahara Desert. Right? Cold Beniguela current, the Namib Desert. Cold West Australian current, the Victorian Desert. Why? Basically, imagine if this is the land and this is the water body. If let's suppose here you have very cold conditions, the air in this region will also be cold, isn't it? So rate of evaporation will be very low. Evaporation will be very low. That means moisture in the air, moisture level will also be very, very low. That means reduced or no rainfall. That means desert. Yes, even the high pressure condition works here. That cold air means sinking air that can create a localized high pressure, means lack of cloud formation, means no rainfall. So wherever across the world you have the cold ocean currents, there you will have no or a desert condition. Thar Desert is obviously not associated with an ocean current. Thar Desert is not closer to the coastline. It is talking about the coastal area. Okay. That brings us to the end of the discussion here. And that brings us to the completion of the fundamentals of physical geography. In an entire lecture series spanning for almost around 17 to 18 lectures, if you are attentive, if you have attended all the sessions and you are not selective, for example, you have what is referred to as the case of visiting students. Visiting students, they will visit one chapter, then fifth chapter, then ninth chapter, and they feel that the entire subject is complete. No, geography is not that subject. If you have attended all the sessions chronologically, you have observed the developments in each one of them. This is a series which is going to help you both for the prelims as well as the mains examination. All that you need to do from your end, just revise. Okay? Let us know how your experience has been in the comment section below. Let us know how, if you have benefited from this, and if you have liked this initiative of ours, give us a thumbs up, click on the like button, subscribe to the channel, and share it with your friends. Till we meet again, and we will meet maybe in a couple of months associated with the Indian geography. Till we meet again, do take care of yourself. Goodbye. Thank you.